Static and dynamic linking are fundamental concepts in software development that determine how external library code is incorporated into programs. Static linking copies the library code directly into the executable during the compilation phase, creating a self-contained program. Dynamic linking, on the other hand, creates references to shared libraries that are resolved when the program runs. In static linking, the process begins with source code being compiled into object files, then linked with static library code to create a complete executable that contains all necessary code. Dynamic linking creates an executable with references to shared libraries. At runtime, the operating system resolves these references by loading the shared library into memory. Understanding the differences between static and dynamic linking is crucial for making informed decisions in software development, affecting everything from program size to update flexibility. Static linking creates a single, self-contained executable file. All the necessary library code is embedded directly into the final program, eliminating any external dependencies. This means the program can run independently without needing separate library files installed on the system. The main advantage of static linking is that it eliminates external dependencies. The program is completely self-sufficient and won't encounter runtime linking issues if libraries are missing or incompatible. However, static linking has drawbacks. It results in larger file sizes since all library code is duplicated in each executable. It also increases memory usage if multiple applications on the system use the same libraries, as each program carries its own copy. Think of static linking like baking all the ingredients directly into one cake. Everything is combined into a single, complete package that doesn't need any additional components. This illustration shows how static linking combines program code, data, and library code into a single file, unlike dynamic linking where the library remains separate. Dynamic linking creates an executable that relies on external shared libraries. These libraries are loaded at runtime. This approach promotes code reuse and reduces the size of executables because multiple programs can share the same library in memory. It's like having a central pantry that all cooks can access. Imagine source code files being compiled into object files alongside a pre-compiled static library. The static linker combines these object files and the static library's code into a single executable. The final executable is independent and contains all the necessary code within it. The important thing to note is everything is contained inside this executable, which is also a key disadvantage when you have more than one of the same executable, as it has to be completely duplicated again. Dynamic linking involves executables with references to functions in shared libraries. The operating system's loader resolves these at runtime by mapping the library into memory. This allows multiple programs to share the same library in RAM, conserving space, though the library must be present on the system. This flow diagram shows the dynamic linking process: source program through translator, linker, and loader, with interactions between object modules and binary programs. The executable holds references to functions in the shared library. At runtime, the loader resolves these by mapping the library into the program's memory space. This diagram illustrates how shared libraries work in virtual memory. Two processes share the same library pages in RAM, reducing memory usage. The library loading process checks environment variables like LD library path and system directories to locate and load the required shared library. Similar to the previous flow, this shows dynamic linking from source to final executable via translator, linker, and loader. Dynamic linking is performed at runtime, with library names placed in the executable image. This enables code sharing and reduces memory usage by storing shared information in virtual memory. Let's create a simple static library called mathlib with add and multiply functions. We start with the source file mathlib.c containing the function definitions. Next, we compile the source file into an object file using GCC. This creates mathlib.o containing the compiled machine code. We then create the static library using the ar command. This archives the object file into libmath.a, our static library. Now we create the main program in main.c. It includes declarations for our math functions and calls them. Finally, we compile the main program with the static library using gcc-llmath. This embeds the library code directly into the executable program. In dynamic linking on Windows, math functions are compiled into a dynamic library known as a DLL. This DLL contains the reusable code that the main program can load at runtime. The main program uses load library to explicitly load the DLL into memory. This function returns a handle to the DLL if successful. Next, getProcAddress retrieves function pointers from the loaded DLL. For example, it can get a pointer to the add function defined in the DLL. The program then interacts with the DLL by calling these function pointers, just like calling regular functions. This allows dynamic access to the library's functionality at runtime. Remember, the DLL library must be present in the program's directory, and the program must be built for dynamic linking. Without these, the program will fail to load or execute properly. Static linking can waste memory when multiple applications duplicate the same library code. Each app contains its own complete copy of the library, leading to inefficient memory usage. Dynamic linking allows sharing libraries across multiple applications, saving significant memory resources. Only one copy of the shared library exists in memory, which all apps can access. This visual comparison shows how dynamic linking reduces executable sizes and enables shared memory usage across applications. Modern systems often use hybrid approaches, blending static and dynamic linking to balance benefits and drawbacks. Understanding these trade-offs helps developers make informed design decisions and choose the optimal linking strategy for their specific needs, considering factors like security, performance, and maintainability.